Okay, I thought I'd insert a video here covering some test equipment that I'm going to use in the next part. First of all, let me go back to part one, and I forgot something. This is, I showed you in a digital photograph how I mounted these diodes. Something else that I do, you may consider it OCD, but whatever, is that I leave 2 millimeters of spacing between the body of the component and the surface of the printed circuit board. So I've got an exposed lead here that I can use for using a digital multimeter probe to measure voltage if I want to. And if I have an oscilloscope, then I can take an oscilloscope probe and also attach here, so that when I power up whatever it is I want to test, I can look at the waveforms, what have you. So something that you might be interested in doing. Also, another OCD thing is, and I think it's funny, is when I mount resistors, I mount them with the banded end at the top, so that when this thing gets crowded, if I need to check a component value, then I can go around and look and read it top down. Simplifies my life a little bit. Okay, last video I showed you a unbuilt audio frequency generator, and here it is assembled. And you can go get these off of eBay. I'm sure you're experienced at buying stuff off of eBay. If not, make sure that you search for the right terms. Sometimes stuff will go away and come back depending on your search string. Also, sort the items from lowest to highest price for the item plus shipping. And then also examine the vendor's location and rating. I always like the high ratings, even if it costs me $1 more, but that's just OCD. On this audio generator, I recommend you buy it with the acrylic case because that protects the item from dust. Plus, you get a nice labeling and what have you on what the jumpers are for, and keeps it from being destroyed when you drop screwdrivers and parts and short things out. Okay, and this thing will run off of 9 to 12 volts. I recommend you running it off of 9. I'm going to run it off of 12 because my 9-volt battery is dead. Also, these little DC barrel connectors, if you have what are called wall warts, the power supplies that plug into the wall that are small, like your USB chargers, phone chargers, etc. And make sure that the voltage is correct, that it's DC, 9 volts plus center terminal. Alright, I'm going to check this, and you can watch me check it. But I looked in my little drawer that has some test equipment, and I had an old item here that I had forgotten about, hadn't used in a while, and this is an audio oscilloscope. They run around $20. It's called a DSO 138. I bought this thing assembled, and I wish I hadn't, because I just spent the last hour fixing solder joints. If I take the display off, it looks like a 14-year-old that works part-time on weekends assembled the thing, and it was the first one they ever did. So I may buy another one in kit form because I believe this touch screen is supposed to allow you to change these trigger points on the scope, but it doesn't work. But that's just whatever. Also, the thing comes with, and I'm using a Rigol probe here because this thing didn't have a probe with it. This thing comes with a test signal that's at 1 kilohertz and 3.3 volts. Didn't tell me whether it was peak or peak to peak, or that was the maximum voltage. Turns out it's 3.3 volts peak to peak. Here's what the signal looks like. It's a square wave, and the manual tells you to adjust these caps to make this square. This has a 12-bit analog to digital converter, which is pretty good for something that's only 20 bucks. Also, this thing either does a fast Fourier transform or looks at zero crossings on a waveform to give you the frequency, 1 kilohertz with 1 hertz accuracy, but you know, take that with a grain of salt. Shows you the maximum voltage, and it's half of 1.3 is 1.65, and that's close enough here. It's oscillating between 1.6 something, too fast for me to see. I can do a hold. 1.71, 1.73, 1.73, 1.69. So that's within 3 to 4%. That's good enough. Okay, now we're going to use this to analyze our signal generator. Okay, here's my signal generator. Let me hook up to the sine wave output. Let's see, I need ground. That always helps to complete the circuit. Come on, hook up. There we go. Let's see if I got this where you can see it. Now I'm going to hook up my handy dandy LiPo battery pack, 11 point whatever volts. And I'm starting generating signal. We can see it here, and I'm going to have to change the time base. But I got this on the lowest frequency in the range of 100 hertz to 8 kilohertz. Let's crank up the amplitude. Let's change my time base to slower sampling. And here I can see that I've got that's the lowest amplitude is like 0.6 to say a quarter of a volt. Let me get it up to a reasonable value here. And my frequency shows to be 147 hertz on the low end. Okay. So, and it's a pretty good sine wave. If I increase the amplitude, let me decrease the sensitivity on the scope. You'll see that I'll get to a point where the sine wave will start to distort on the high end of the amplitude adjustment on the signal generator. Also on the signal generator, counterclockwise increases the amplitude. It's opposite of what I'm used to on most equipment and controls. Okay, 147, let's go to the high end. And it's supposed to be like 8 kilohertz, but I'm going to have to change my scope sampling. Oops, wrong way. I had a 50-50 chance, didn't I? Okay. Do I want to? Yeah, there we go. And it shows that it's what? 8. Oh, I hadn't got all the adjustments. Shows to be. I got everything maxed out here. Shows it only goes to like 4 kilohertz. But I can get that on the next range, starts at 3. So let's go to that range. Alright, so there's 3.3 1/4 there. Now this thing goes up to 65 kilohertz. See if I can get, there's 8, 9, 10, 11, 12, 13, 15, 16, 28. Whoops, it got to, well, 65 is 40, 50. Okay, I got to this point here, and I need to sample a faster rate. Is that right? 20. Oh, I'm going the wrong way. See, I already got a 50-50 chance of getting this right, and I blew it. Okay, high end here is about 90 kilohertz. But it's close enough because I got another higher range. I'm going to go to the low end of it, and it's at 60 kilohertz. Let's go up to the high end. Now the scope samples at 200 kilohertz, so that means that the Nyquist frequency is 100 kilohertz, and I expect this thing to fail when this gets to 100 kilohertz. 90, 78, 90, 91, 92, 94, 97, 100. Okay, it goes, oh, it can sample above that. But what happens is what's going to happen is this voltage reading here is going to be off. Let's see here. This is going to be nice because oh, that's the fastest. 10 microseconds is the best I can do, but let's see what happens if this thing goes to 200. Nope. Okay. But it's only good for like 200 kilohertz. Excuse me, 100 kilohertz, but I can get a little extra out of it if I need it. But it's not going to be enough to do the 455, so we'll have to do something different there. Okay, so I've got two pieces of test equipment that we're going to be using. One is the oscilloscope, the other is the signal generator, and the frequency counter. Remember I pointed to the little $10 frequency counter. Let me power it. Let's see, I need another power supply here. That's the trouble. So I got another LiPo battery. Okay. Let me hook up scope to the input, scope probe to the input of the frequency counter. Hook it up to my signal generator. Now remember, my signal generator is supposed to go to 1 megahertz, powered up. Let's look at the high end. Crank up the amplitude, and looky there. Signal generator will generate up to 1.3 megahertz, and if I crank it down, okay. Now why this is important is that I can go to 1300 on my AM dial with my audio generator. So I'm getting into the low RF, 1 megahertz. Let's see how low this thing will go. Signal generator will go to 200, 180, 160, 130. Now, the signal generator goes, down to 1 hertz, but my frequency counter fails at, or stops displaying at 100 kilohertz. Two reasons for that. One, it's designed for RF, and the input circuitry has isolation capacitor to keep you from zapping the counter when you put a DC voltage in here that exceeds the operating voltage here. So if I increase the input cap here or increase the input amplitude, I can read lower, but you shouldn't be doing that, so it's good enough. Just to demonstrate that I can measure RF with this counter, which only cost me $10, and it's good down to 1 hertz. I took this one when I got it and hooked it up to a rubidium 10 megahertz source that was good to 0.005 hertz, and this display went to 10.000000. So it may be off 1 hertz now, but it's good enough for RF radio amateur work, etc. That's it. That's my test equipment. Just wanted to show you some items that you may be interested in your lab, and you'd probably only want to do that if you want to get serious about electronics. So thank you for your time. We'll go on to build the next, the audio section of the AM radio.